Hello and welcome to the Werder Scientific webinar on additive manufacturing. My name is Raina and I am part of the marketing team here at Werder Scientific. And it's also my job today to guide you a little bit through the program of this webinar here. I hope you all did not have any problems logging in, and the technology is also working so far, which I know can be kind of tricky sometimes. But however, if there are any problems with the connection and you are kicked out of the webinar and can no longer log in, or have problems with the picture or the sound and stuff like that, that is not the end of the world. After this webinar, we will provide all participants with a download package that contains a recording of the entire webinar session and some other things that may be interesting for you. So you won't miss a thing, I promise. So to start with, of course, you have the chance of asking questions at any time during the webinar, and we will answer them directly as far as possible. My colleagues here are looking forward to answering your questions. But however, if we don't have the time to answer all the questions that come up, that won't be a problem either. Nothing will be lost here. Open questions will be answered individually by our specialists after the webinar. I would just ask you to be patient for a day or two, but everything will be answered. You will get an email with your answer, and yeah, so don't worry. So how to ask questions? For those who may be attending a webinar for the first time today or are not familiar with the GoToWebinar software, here you can see a screenshot of the GoToWebinar control panel. Unfortunately, it's in German, but apart from the language, it should look similar on your screens too. You simply type your question down here in this field and the question will be answered privately. Questions are not posted publicly and are only visible to the moderators. So please don't be shy. If you have a question, feel free to ask. Okay, let's move on to today's agenda. The webinar will start with a brief introduction, which we are right in the middle of. And I will tell you a little bit about Werder Scientific and our group of companies and the manufacturers. And then we will get straight into the actual topic, namely, what solutions do we offer in terms of quality control and post-processing for additive manufacturing? Starting off with my colleague, Dr. Gerhard Beckers from RETSCH, we discussed the topic of particle size reduction and particle size separation in additive manufacturing applications, which deals with both the quality control of raw materials and the recycling of scrap material. Jörg Westermann from MICROTRAC MRB will then talk about the characterization of metal powders in additive manufacturing. Here, in particular, about the topic of size and shape, density, surface area, and porosity. After that, Dr. André Klostermeier from ELTRA will then take over and report on the equipment we offer in the field of elemental analysis as part of quality control. And to round off the topic, Dr. Tim Ohnweiler from Carbolat Gero will talk about the heat treatment of additive manufactured components, which means debinding and sintering. And last but not least, we will hear from Paham Gemagami from QATM on the subject of metallographic preparation as part of the quality control process in additive manufacturing. Good. I've already mentioned Werder Scientific quite a few times, but if you've come to this webinar via a newsletter invitation from one of our manufacturers or via their website, the name Werder Scientific probably isn't that familiar to you. So I would therefore like to briefly introduce ourselves. Werder Scientific is the umbrella, so to speak, under which our manufacturing companies ELTRA, Carbolat Gero, RETSCH, MICROTRAC, and QATM come together. And this umbrella is relatively large. We have 10 locations worldwide where development and production takes place and around 22 sales offices of our own. We employ around 1,300 people worldwide. So, but let's now get a closer look on our brands. Carbolat Gero is a leading manufacturer of high temperature furnaces and ovens from 30 to 3000 degrees C with a focus on a vacuum and special atmosphere technology. And with more than 80 years of experience in thermal engineering, their products are used in research laboratories, pilot plants, and manufacturing sites worldwide. The presenter for the Carbolite Gero part in this webinar will be Dr. Tim Ohnweiler from the International Sales and Product Development Team. ELTRA is one of the world's leading manufacturers of elemental analyzers for rapid and accurate analysis of solid materials. Their elemental analyzers provide tailor-made solutions for a wide range of samples and concentrations. ELTRA's part in this webinar today will be presented by Dr. André Klostermeier, who is Product Manager and Application Specialist. RETSCH offers instruments for sample preparation and characterization of solids. They develop size reduction and sieving equipment, which is known for its excellent performance and operating convenience. The presentation will be held by Dr. Gerhard Beckers, longtime member of the RETSCH application team. MICROTRAC's product range offers solutions for particle characterization like size and shape, gas adsorption, surface area and pore size distribution, density measurement, and a lot more. Jörg Westermann, member of the International Sales and Product Development Team, will give you some more insights today. QATM is one of the leading companies for materialography, metallography, and hardness testing, and supplies both instruments but also complete laboratories, software, and consumables. Here, Parham Gemagami, member of the QATM Product Management and Application Technology Team, will hold the presentation. So, as you can see, our companies cover different fields of applications which have one thing in common. They are all part of the quality control process in many industries and, in some cases, are also used in the production process. And what a great coincidence, additive manufacturing is a typical example for that. In the quality control of raw materials like metal powders, MICROTRAC analyzers are used to determine particle size and shape, and ELTRA analyzers measure the carbon or oxygen content of these powders. Carbolite furnaces are employed in post-processing for debinding and sintering, and then ELTRA again comes into play when the element concentrations of the final components are analyzed for quality control. This interdisciplinary approach within our group of companies means that we can offer you as our customers holistic solutions which take into account the whole process and not just one aspect. Here you can see that instruments from our manufacturers can be found in many parts of the additive manufacturing process chain, but more on this in the individual presentations. The slots in this webinar are relatively short, but they will give you a concise overview of our products for additive manufacturing. You are welcome to get in touch with us for any further information you may require. So please just contact us if you have any questions or get to know a little bit more details and stuff like that. Besides that, our manufacturers hold webinars on a regular basis and on a wide range of topics. So if you don't want to miss anything, make sure to subscribe to our newsletter to keep up to date with the latest information on new product developments, exhibitions, interesting applications, and of course, also webinars. The easiest way to do this is to visit our website and register for our newsletters. So please just visit verda-scientific.com, and here you can select news and then newsletter registration. And on the following website, you can subscribe for any of our newsletters, for all of them, for some of them, as you like. And yeah, we're looking forward to keep in touch with you. So, okay, with that being said, and having introduced Verda Scientific to you a little bit more, let's start with the presentation of RETSCH. Gerhard, please take over.
Yeah, thank you, Rena, for your nice introduction. And I would like to welcome you to our presentation about additive manufacturing. I would like to directly start with the presentation about particle size reduction and particle size separation for different kinds of applications in additive manufacturing. When we talk about additive manufacturing, this covers various kinds of powders, and these powders can be plastics, ceramics, or even metals. And these materials can have different sources, so that the materials can come from recycling, like defective products which have to be removed into the process, or waste products like sprues from injection molding, but also raw materials have to be prepared in front. So this preparation means the particle size has to be reduced or just analyzed or separated. And here we talk about clearly defined particle size ranges. So that can be millimeter range or even micrometer range. So when we talk about particle size reduction, that means that the particle is ground, broken, milled, whatever. And I've got 3 examples here for you. And I would start with the green bodies. So green bodies, like here, for example, made of metal, but also feedstock, or as shown here, a resin can be reduced in size. Starting with the green bodies, there was a task to grind this, let's say, pressed metal of several kilograms down to a size of below 2 millimeters for a recycling process. But as these particles can be very hard, we need a strong machine to grind this material. And here we have used a jaw crusher, a BB500, and we have set this machine to a gap size of 1 millimeter. That means the particles has to pass a gap of 1 millimeter, and then they need to be ground, they break down. And with this machine, we were able to grind this several kilograms within a few minutes down to 2 millimeters. So what happens inside a jaw crusher? As you can see here, this is another jaw crusher shown, but this just shows the grinding mechanism. The particles drop from top into this hopper into the grinding chamber. And there's one jaw which is moving and is decreasing and opening a gap towards the other jaw. And then the material drops into this crushing chamber and is ground by pressure between the 2 jaws until this material is fine enough to pass the gap at the bottom and drop into the collecting receptacle. And depending on the setting of these jaws and the breaking properties of the material to be ground, you can create a very broad range of particle sizes. As seen before, here it was down to 2 millimeters. Another application is the recycling of the preparation of feedstock. So this is, well, frankly speaking, just a pressed powder into agglomerates, but these big chunks are too big to be processed further on, so they also need to be decreased in size. But here the task was a bit more difficult, because for a injection molding or for extrusion process, we need to grind the particles down to a few millimeters, but we had to avoid the generation of fine powders. And this is quite difficult because it's easy to grind smaller than, but you always have got lots of fines in your sample. And so we used the cutting mill for this purpose to grind the feedstock down to 3 to 4 millimeters. And with a bottom sieve of 8 millimeters, it is quite easy to create a size of smaller 4 millimeters. But the difficulty again was to avoid the fine powder. And there the cutting mill SM300 is a good choice, because this machine allows to set the revolution speed of the rotor from 100 to 3000 RPM. And at a very low revolution speed of 400 RPM, we reduce the impacting of the material against the grinding chamber. And so the grinding takes place mostly by cutting and not by impacting. So the particle sizes are precisely defined. So as you can see here in this photo, there are very low amounts of fines, but the gross material is in this range of 3 to 4 millimeters. So what happens inside the cutting mill? Here's a short video about the principle, where you can see the sample drops in to the hopper, and then it enters the grinding chamber, where a rotor is rotating at a set speed. In this case, it was 400 RPM. And while the material is rotating, it is cut between the knives and the cutting bars. And this takes as long, I'm just going back, As it is fine enough to pass the sieve, which is placed in the bottom here, so all the material can drop down afterwards into the collecting receptacle from which it can be taken for the next step. So just switching to the next slide. Another application was grinding of resins down to a micrometer range. So this also is easily possible, but you need a special machine for that. In this case, it was a resin with the size of 2 to 3 millimeters. And that had to be ground down to less than 50 micron to allow a use for 3D printing. And we need this small size to avoid the clogging of the nozzles. And then we need a very fine powder. And here we have used an ultracentrifugal mill, ZM300, with a revolution speed of 18,000 RPM. So this is a very high speed. I will tell you later on what this means. And using a ring sieve of 0.12 millimeters allows us to grind more than 60–70% of the material to less than 50 micrometers. So what happens inside the ultracentrifugal mill? Here you can see the machine opened. And inside the machine, you find a small cassette, a metal cassette. And inside this cassette, the grinding takes place. Normally, this is closed and the material drops in from top into this cassette. So what happens during grinding? So the material drops in either manually or with a feeder like shown here into this cassette. It enters the grinding chamber where the rotor is rotating at very high speed, and this causing the sample to impact against the rotor teeth, and subsequently it is ground by shearing along the sieve which surrounds the rotor. And depending on the opening of this sieve, you can create very fine powders or eventually even coarser sizes. And then the sample can be taken by just taking out the cassette, and you got your fine powder to be used for the next step. But as I mentioned in front, we have used for the resin, for example, we've used a sieve of 0.12 millimeters, and we were able to grind 60–70% below 50 micrometers. But as said, we need all of the material being fine enough to avoid clogging of the 3D printing nozzles. So then sometimes it's necessary to remove oversized particles. And this can easily be done with a sieve shaker. So what does that mean? We've got a possibility to use sieves to separate particles. So either you separate these particles with a certain sieve size, but you also can completely analyze the particle size distribution of your sample. And here we are talking about the micrometer range. And here I show you just a example of the separation of a metal powder, where particles of bigger 53 micrometer had to be removed in terms to allow the use of this fine powder for 3D printing. This now shows a complete protocol of the sieve analysis. We've got detailed information about the complete process, like the information of the material, the kind of process, sieving process, the machine that has been used, and lots of other information. Most important, you get a tabular result at the end, where you can see how much of your particles are smaller at a certain size. In this example, 67% of the whole powder is being smaller than 38 micron. And on the other hand, you see here, for example, that 2.5% of this powder is bigger than 53 micrometers. So we were able to remove this fraction of bigger particles from the whole sample, that we were able to recover 97% that then can be used for the 3D printing process without any problems, of course. It's also possible to get lots of other information or characteristics which can be individually set in the software to be calculated and give you more information about the particle size distribution of your product. Okay, so this is just a sieve analysis or the result that you can see. How is it produced, this result? So for this purpose, we use a so-called sieve shaker. And the sieve shaker is used to take a lot of sieves. Here in this example, we got 8 sieves on a collecting pan. And the sieves are set up in a descending order. So that means we've got a big sieve on top and decreasing mesh sizes in the other sieves. So that means the material which is placed on top of the sieve is then just, let's say, agitated with the sieve shaker and comes in motion and can pass the mesh when it's smaller than the opening. And particles that are bigger are just retained on that sieve. And this allows us to completely separate the particles in terms of size. So we get various fractions between these limits. And this is done with a sieve shaker. That means this whole sieve stack is jumping up and down, as this is shown here. That means with this vibration, the particles start to jump, as you can see here, in real motion. And this allows the particles to completely rotate and can be compared with the mesh in another orientation. And so you are able to separate all the particles by moving them very strongly. And this is done with this electromagnetic drive. And as we use electromagnetic drives, you've got a very quiet operation, which is also very comfortable to be used. So far about the possibility to separate particles with sieve shakers. This is just an excerpt of what we are able to provide as a solution for your applications, but we also have got lots of other application fields, not just plastics, metals, or resins, but also shown like in this screen here, different other application fields. I would like to point out that it's also important for you to know that you do not have to just refer to general information. You also can send us a sample for free of charge testing that can be either grinding in our application laboratory or also sieving, so sieve analysis can be performed. You just have to fill in a questionnaire and type in all your demands, and we will take care to find the best solution for your application, so that we do something like a method development that can be directly used at your site. So feel free to just send us a sample. Further information, of course, can be taken from our website, so that you can find lots of information about milling, as been seen before, but there are various other machines that can be used for grinding, not just draw crushers, cutting mills, and rotor mills, but also ball mills and different other grinders and mills. Or sieve analysis, you get information about sieve shakers and the way how to analyze and to protocol, document these analysis, and assisting how to have all these other machines like feeding kits or like sample dividers that can be used for processing the sample in front. But we also have got lots of recordings of other webinars and different information about our machines, like detailed information about their possibilities and use. So just take a look at our homepage for further information. I hope you got some details about your application, but in case you haven't found what is important for you, again, feel free to contact us directly, or you can type in your questions here in the chat function, and we try to answer these directly, and hope to get hope you're happy and get information for you available. Thank you for your attention, and goodbye for now.
So thank you, Gerhard, for this introduction of RETSCH and RETSCH's role in the additive manufacturing process and what RETSCH can do for this process and for quality control. So I think we move on in our schedule and hear from Jörg Westermann from MICROTRAC MRB next about the characterization of metal powders in additive manufacturing. Jörg is member of the international sales and product development team from MICROTRAC for some years now. And yeah, so please, Jörg, tell us more.
Thank you, Rainer, for the very nice introduction. So it's my pleasure now in the next 15 minutes to guide you through the products that MICROTRAC MRB is offering for the 3D printing community. That means we will speak basically about the characterization of metal powders with respect to the size and shape of the particles, as well as density, surface area, and porosity. My name is Jörg Westermann. I'm working for MICROTRAC MRB since 17 years. And I'm working as a product specialist and have some experience with the metal powder and our customers in the metal powder community. So in this presentation, we will be talking about ISO ASTM 52907, which explains methods to characterize the metal powders for 3D printing. And we will also mention some other ISO standards which are related to density, surface area, porosity of metal powders and additive manufacturing parts. Our customers in the additive manufacturing community come from the whole value chain. So our instruments are being used by the powder manufacturers, for example, such as Böhler or Carpenter or Höganäs. We sell to the printer manufacturers, such as companies EOS, Trumpf, DMG Mori. We sell to companies which produce atomizers and powder handling systems. We sell to companies that produce the parts, that use the printers and the powder to manufacture 3D printed parts, such as automotive companies or aerospace companies. And last but not least, of course, we also sell our instruments to research institutes such as MTC in the UK, RISE, Sverige Kimab in Sweden, Korean, Singapore, Chinese, US, and German institutes and universities. So why is particle size and particle shape analysis important for additive manufacturing? First of all, it's about the packing density. So when we have powder with a size distribution which is nicely wide, then all the gaps between the bigger particles can be filled by small particles and we achieve a good packing density. If we have only small particles or only big particles, then this cannot be achieved. Also, the oxide content, that means how much surface area do the particles have, how much contamination is on the surface, depends on the particle size distribution, on the particle size of our powder. Surface roughness, layer thickness, the additive manufacturing in many cases is a layer by layer process, and of course if we have large particles we cannot achieve thin layers. The parameters of the laser beam also depend on the properties of the powder. If we have larger powders, we need a different energy to melt the particles than we have smaller powders. And last but not least, we are creating layers in the manufacturing machine, and the flowability of the powder has a big influence on the homogeneity of the layers. So if we have a nice flowing powder which consists of round particles with a small number of satellites, then we can achieve a more homogeneous layer than if we have irregular shaped particles. In general, there are always exceptions from the rule, but this is the basic idea. So when powder is sold or powder is purchased, the powder quality is checked, and density, particle size, particle shape are important parameters to understand if the correct powder is being used. For the size analysis, 3 different methods are recommended by the standards and guidelines. And the key methods which are used in the field is sieving, is dynamic image analysis, and laser diffraction. So our product portfolio covers all these 3 methods. Our sister company RETSCH is selling sieves and sieve machines, and MICROTRAC is having the complementary dynamic image analysis and laser diffraction. So when we look at the different methods, we can see that the methods have advantages and disadvantages. We can see, for example, that when we look at the width of the dynamic range of the particles, so we have small particles and large particles. If the small particles are much smaller than the big particles, then laser diffraction is the method of choice. The sieving and cam sizer cannot measure such a wide range of particle sizes. However, for additive manufacturing, particle size range is typically from 5 to 45 microns, or maybe 5 to 150 microns. And in this range, all the different methods provide good results. Repeatability and reproducibility is also an important issue, important topics, as well as the resolution. If I have mixes of particles, mixes of different samples, by dynamic image analysis, I can see the blend of powders more clear than by methods like laser diffraction or sieving, where the resolution is not as high. Particle shape analysis is a unique feature of the image analysis. Particle shape analysis cannot be done by laser diffraction or sieving, and the dynamic image analysis also offers the possibility to emulate the results which are produced by sieving. So if the old way to measure the size distribution was a sieving method, then with the imaging method, we can get results which are very similar to the sieving method. With the laser diffraction, it's generally not possible for all different types of particles and particle shapes to get the same results like the sieve diffraction. An important topic is contaminations. So very often in our 3D printing powders, we have small amounts of large particles or small amounts of particles with the wrong shape. And with the image analysis, we can detect these outliers very reliably. The sieve shaker can also detect particles which are too large, and the image analysis can detect large particles as well as odd-shaped, bad-shaped particles like needles or flat particles. Operation of laser diffraction and image analysis typically is much faster and much easier than the sieving operation, which needs more time, it's much more time consuming. So the measurement speed for image analysis and laser diffraction is higher, and the big advantage also in the dynamic image analysis, we can see the results for individual particles. So we can measure not only the size, but also the shape of the single particles. So how does the dynamic image analysis work? Basically, what we do is we have a camera and we let the particles move in front of the camera. This is the basics for the dynamic, in the name dynamic image analysis. Yeah, we have a camera at a fixed position and we are moving the particles in front of the camera. In reality, what you do is you take a teaspoon or 2 teaspoons, maybe 5 to 15 grams of metal powder, put it in a funnel. Then we have a hopper. The material is moving on this hopper, falling into a small funnel. And with the air pressure, the particles are dispersed. That means we have single particles, not many particles at the same time. Then these single particles are flying through our detection area, where we measure the particle size with 2 cameras, and then the particles are collected in a vacuum cleaner. This way we can measure the size of the particles. For example, we can measure the thickness of the particles or the length of the particles. Of course, if we have nice particles like the round particle here in the middle, then width and length is the same. But if we have irregular shaped particles like here the particle on the bottom, then we get different values for length and width, and both numbers are interesting to get because they tell us if the material is nice and round, is homogeneous, it will be nicely flowing, or it will be a particle that creates problems when we create our layer in the printer. The dynamic image analysis very often allows us to see the picture of the particle, and we can see the numbers which are calculated for this single particle. And we can calculate, of course, the size of the particles, but also we can calculate numbers which describe the shape of the particles. For example, here the width to length ratio, and this tells us, yes, we have nice round particles, or no, we have irregular shaped particles, we have satellites on the particles, and we can see the quality from one batch is the same as the quality of the next batch. The dynamic image analysis works independent from the material type that we have. We can measure all types of metal powders which are commonly used in this 3D printing. It doesn't matter if we're looking at titanium powders for medical applications, or we have steel alloys or nickel or tungsten. All types of metal powders can be measured by the dynamic image analysis, and both the percentage of the particles versus the particle size and the percentage of the particles versus the particle shape can both be measured independently. So I can see how many particles are large and how many particles are small. Do we have too much dust in the sample? But we can also see, yes, all our particles have a nice round shape, or we have a lot of irregular shaped particles in our sample. Second method that I want to mention today is the laser diffraction. What happens here is we shine laser light onto our particles. When the wave of the light interacts with the particle, we have diffraction, refraction, absorption, and reflection. And this diffraction for the big, relatively big metal particles causes a diffraction pattern, and this is what we measure. So we measure the light intensity and the direction of the scattered light. And from this, the instrument calculates the size distribution of all particles, because the big particles scatter the light into forward direction and the smaller particles scatter the light sideways. The instrument for the laser diffraction is the so-called sync. The previous model was called S3500, and the S3500 actually has been used in many quality control labs for the metal powder community, so it's maybe a very common instrument there. The latest model is called MICROTRAC Sync. These instruments feature both instruments feature the same laser setup. So we have laser light which shines on the sample. At the sample, the light is scattered. We are using 3 lasers from 3 different directions which scatter the light on 2 detectors. And in addition, the camera allows us to measure the particles in images. So we can see images and scattering pattern, and we can calculate laser diffraction results and imaging results at the same time. So this is a very unique combination which is not available in any other instrument. The results that we get is basically the size distribution from laser diffraction experiment. So we get the percentage of particles which are smaller than a given size, or we can get the derivative distribution. Both it's just a matter of calculation. And in addition to the size distribution with the sync instrument and the integrated camera, we can also get pictures of our particles, and we can see also if we have nice and round or more irregular shaped particles in our sample. In addition to particle size and shape, MICROTRAC offers also measurement of the density of the powder. Here we have an instrument called Bell-Pigno, and what we do basically is we give a certain mass of powder into a sample chamber. Then we load the sample chamber with gas, and the pressure which results, the pressure that we measure, tells us how much volume in this sample chamber is occupied by the particles. So this is typically done with helium. So this is a helium picnometer. In addition to the density, also in many cases, it's interesting to study the surface area of the particles, or how large is the surface area of the particles, because the surface area tells us about the possible particle-particle interaction. The more surface area, the more reactivity, the more interaction, the more contamination, water absorption, and also oxide layer on the surface we may have. So the surface area is analyzed by the so-called BET method. The instruments for analyzing the surface area are the so-called Bell-Sorb Mini-X and Max-X. These instruments use the procedure from Brunauer and Teller, BET, for studying the surface area. Basically, what happens is you cool the sample to the temperature of the liquid nitrogen. Then nitrogen molecules are let into the chamber, and these nitrogen molecules are condensing on the surface of our sample, because it's the temperature where they freeze, basically. And then the surface is covered slowly but surely by these nitrogen molecules. So when we let in few molecules, small area is covered. When we let in more molecules, then the coverage of the surface becomes larger and larger, and also the smaller and larger pores finally are filled with the nitrogen molecules. And from this, we can calculate the surface area. If we calculate the respective isotherms and the BET plot, from the BET plot, then we can calculate the surface areas. Here, this example shows the measurement of 6 different aluminium samples. And here the trick is really that these aluminium samples have a quite small surface area, and therefore, instead of using the nitrogen, we use krypton gas. Last but not least, it's also interesting, especially also if you have printed parts, to study the porosity of the material with mercury porosimeter. That means we have liquid mercury, and we apply some pressure to press the liquid mercury into our sample material. The sample material, as I said, it could be the powder. The powders usually are quite compact, but it could also be a finished part. So we press the liquid mercury into the part, and we can study at which pressure the pores are filled. If we apply a low pressure, the liquid mercury will go into the large pores, and the higher the pressure, then the smaller and smaller pores can be filled. We have 2 different instruments for this. There's an instrument for the lower pressure range and an instrument for a higher pressure range. Okay, I think that's it. And if you have any questions, let us know, and I would be happy to answer your questions. Thank you for your attention.
So thanks a lot, Jörg, for this introduction of MICROTRAC. And I think we will move on in our agenda and now hear from ELTRA and André Klostermeier, who is product manager and application specialist on ELTRA's elemental analyzers for quality control in additive manufacturing.
Thank you, Raina, for the nice introduction. And yes, I would like to start with the ELTRA presentation. Yes. Elemental analysis for quality control and additive manufacturing is a big issue for us, and we can provide several solutions which makes the quality of your powders and your products a little better. And now I would like to start with my presentation. just let me give you a short structure, what we are talking about. First, I will introduce ELTRA. Maybe you know us or maybe you are not. Then I will just give you a short ideas what does mean ELTRA analysis and quality control in the additive manufacturing process. Then we will talk about the most prominent, I would say, analysis topics for us, which means analysis of carbon and sulfur and analysis of oxygen, nitrogen, and hydrogen. Yes, of course. And then at the end, we will have a short summary, and then we are finished. And yes, let's start. ELTRA is a company which is located in Hahn. It's near Düsseldorf. We have been founded in 1981, and our portfolio is combustion and inert gas fusion analyzers. And we are focused on the analysis of carbon and sulfur and the oxygen, nitrogen, and hydrogen content. And in addition, we also have thermogravimetric analyzers. For additive manufacturing, usually the carbon sulfur content is of interest, as well as the oxygen, nitrogen, and hydrogen content, because these elements influence the properties of powder as well as the finished products. Our functional principle of all analyzers is always the same. It does mean we have a sample, put some energy on it, and then the sample combusts or is burned or it melts, however it is destroyed. And during the destruction process, we have some carrier gases, which usually mean oxygen or nitrogen, or maybe also just helium as carrier gas. And then we are measuring the released gases, which could mean CO2, SO2, and also hydrogen and nitrogen. We always have a destructive analysis, and we are always analyzing gases in the sample. This is the common principle. But keep in mind that depending on your sample, or maybe depending on the requested analysis, the applied technique is a little bit different, and I would say all settings for the analysis are a little bit different. But however, we can provide full solutions, I would say, for every common sample. So what we are doing in additive manufacturing, due to the fact that we have some customers in the field and we processed a lot of samples, we have a large experience for a lot of samples, and we can give you, I would say, a good application note and settings for every sample. Just let me give you a short overview where we are present. We are present on the one hand for the analysis of raw material, and on the other we are also present for the analysis of the finished material. You see the figure here below is what made from titanium powder from the sample from a customer of us. And for the raw material, it is, I would say, first easy. You can have a look at the, I would say, ASTM standard, which means 52900 It describes the different processes which are relevant for additive manufacturing powder. It describes sampling, particle size distribution, chemical composition, and also other characteristics like morphology or contamination, flowability. We are responsible, or our ELTRA analyzers can be used for one topic, and this means chemical composition. And when you have a look at the chemical composition, we are also focused on only 5 elements. These elements are very, very relevant, but it's only a small part of powder analysis. And when you choose your powder and make your product, however, what does mean? For example, maybe you are in the field of medical applications or aerospace or whatever. Then you have your finished product, and then for this finished product, you sometimes also require a carbon sulfur or oxygen, nitrogen, and hydrogen analysis. But this is only related to your product. Nobody knows if you really have to do this, but it's a recommendation, and sometimes you have the need for it. Yes, what is, I would say, the one of our biggest, which element has the biggest influence? This is nothing you can say, this is the most relevant element, but especially for medical products, hydrogen measurement is a little bit more important than other elements, because then you have the effect of hydrogen embrittlement. And when you say that you, for example, are doing medical things, then a brake inside the human body would be really dramatic, and this is something you would like to avoid. And you cannot predict which influence has an element for every matrix, but the general things are carbon influences technical properties like melting points and hardness. Sulfur influences the machinability. Oxygen is an indicator for, I would say, good tendency for corrosions. Nitrogen can influence the hardness. And as mentioned before, hydrogen can dramatically influence the stability of a product, which means, is this product really stable when you use this? And for this reason, hydrogen analysis is highly recommended, especially for aerospace and medical applications. What does this mean in detail? As I mentioned before, we have to provide different solutions for carbon sulfur and oxygen, nitrogen, hydrogen analysis. The usage of our analyzers is in sum very easy. So I just show you some pictures and give you a short idea how our samples can be, or how your samples can be processed in our analyzers. You just have to log in a sample in the software, weigh the sample, add some accelerators, then put the crucible on the pedestal of the analyzer, start analysis in the software. Then the sample is combusted, it's detected in the air cells, and then you get your results. That's all. So this process of analysis can, on the one hand, be performed by academic skilled persons, but on the other, it can also be performed by not academic skilled persons, because for routine analysis, you don't need, in general, an academic skilled person. And that's it. You don't have to consider a lot of more. The basic things which are important for carbon sulfur analysis with ELTRA is the general application settings. We are free to analyze every form of samples, which does mean you can apply powder, you can apply drillings, chips, granule samples, or solid samples in any shape. And this is a big advantage of this technique. When you are used, for example, to perform measurements with optical emission spectroscopy, you usually have to provide a special sample shape, and or maybe have you take your sample and disintegrate it in acid. But for combustion analysis, it's very easy. You just took your sample, put it in the crucible, and then you have to apply your accelerator. And on the left side of the table, you see what are our typical matrices, which means steel, iron, copper, nickel, and titanium. The only thing which is important is the maximum of amount you have to apply to the crucible, which means 1,000 milligrams for steel, or maybe 300 up to 500 milligrams for a titanium-based sample. And that's it. You just have to apply your accelerator, stat analysis, and that's it. And just to give you an idea about typical results, and yes, we have nickel powder, and which was analyzed in ASTM test cycle. We get this powder, put it in our crucibles, add the accelerator, just 1.7 gram of tungsten, put it on the pedestal, and run all these samples. And these are the typical measuring curves you see here. You see, maybe it's a little bit weak. You cannot see perfectly, but carbon sulfur analysis in some needs 1 minute, or approximately 1 minute and 90 seconds. But the total measuring time for a typical sample is about 45 seconds, which you see in a computer. Everything else is flushing the sample and cooling down time. And within this 35 seconds, you can get a reliable result for nearly every sample. And here you see what we get. We had a nickel alloy, which is the standard, where we get concentrations about 0.03% of carbon. And then we also have this iron nickel feedstock. We also get an analysis of 0.0182% of carbon. These are typical results for these samples, but nevertheless, you can also get reliable results for higher and lower concentrations. The application do not have to be changed, and you can make a reliable analysis for a lot of samples which you get in your laboratory. But usually you are fixed to some special, I would say, feedstock samples, so you expect always the same concentrations. And that's it for carbonate sulfur analysis. You don't have to consider more. ONH analysis is a little bit different. This is just due to the fact that you have to consider that you have to remove oxygen and nitrogen, which is really present in our atmosphere in a large amount. Because on the one hand, you lock in the sample again, weigh your sample, apply the sample, but then you have to apply it to a sample port, which can be flushed with inert gas like helium. Then again, you start analysis. Then we have a preheating of a crucible. Then we have some chemical reactions. And then we have a different detector than this kind of analyzer, which means we have on the one hand ER cells, but on the other an TCD cell, which is responsible for nitrogen and hydrogen measurement. Yeah, and that's it. It's again like usage by academic skilled persons and not academic skilled persons. For steel and iron, we again have a maximum amount of about 1000 milligram. It's not limited to powder or solid samples. You can also apply drilled samples or chipped samples. It's no problem. For titanium analysis, you have to consider the ASTM regulations, which does mean 100 milligram is the maximum for N analysis and approximately 300 milligram is the maximum for hydrogen analysis. This is not due to our analyzers, but it's just due to regulations of the standard. And the application of different forms, it's easy, and a solid sample is applied directly to the furnace, and powders or drilled samples just have to be applied in capsules. Yeah, and that's it. Typical results again look like this. For oxygen and nitrogen determination, you can have a simultaneous measurement, which means here you have a blue curve, which is the measurement of oxygen. Then we have the yellow curve, which is the measurement of nitrogen. And here again, we have processed the iron nickel feedstock sample, and which came from a customer. And there you see that we get typical results of 0.05% of oxygen and 0.03% of nitrogen, and approximately 12 ppm of hydrogen. Hydrogen is done in a different measurement because in ONH analyzer we have on the one hand a measuring mode for oxygen nitrogen and on the other measurement mode for hydrogen. This is also related to some regulations which are fixed in some ASTM standards. And as you can see here, like carbon sulfur analysis, oxygen and nitrogen analysis could be very, very precise, and is very easy for all kind of samples and all kind of, I would say, sample shapes. Yes, and this is the reason why I can just come now to a summary, because in detail it may be a little bit different what you have to do for your samples, and details you have to consider, because sometimes we get powdered samples which are maybe based on rare earth materials, or maybe you have very cost-intensive samples like silver or gold, and there you have to consider all sometimes other details. But in some, you take your sample, combust it in an analyzer, and measure the released gases. And this is the same for solid samples, powdered samples, drilled samples. And it also does not matter if you have a titanium-based sample or if you have an iron or nickel-based sample. We are doing always the same, but maybe sometimes we have to consider a lot of small details. But however, this procedure is safe. It's, I would say, published and recommended by the ASTM standard, and it's also regulated by a lot of ASTM standard. And when you would like to have, I would say, a measurement for your samples, or would like to, I would say, have an idea how is the composition of your sample, then it's very easy. Just visit our homepage. Then you can get in contact with ELTRA, and you can send us our samples, and we can perform, I would say, nearly everything you have in your lab. Or maybe we have to say, okay, in this case, please consider this and consider that. And As you see here, the application at all is safe and is very easy. And when you would like to be in contact with us, just write us an email and then that's it. So I would like to thank you for your participation of the webinar. And after all, I would say I would like to hand over to Raina again. And please also have a look at all other webinars which are taking place today. And yes, after all, that's it. Thank you.
Yes, thank you, Andre, and thanks a lot for introducing ELTRA in our webinar today. Let's move on to our next slot, which is Carbolite Gero, presented by Dr. Tim Ohnweiler from the International Sales and Product Development Team. And Tim will talk about heat treatment in additive manufacturing, debinding and sintering. Tim, please.
Okay, thank you very much for the kind introduction, Rena. Yeah, as Rena already kindly introduced, I will present what Carbolite Gero can do for additive manufacturing. And basically in additive manufacturing, everyone thinks about the printer. An often underestimated process step is heat treatment. And Carbolite Gero is focused on heat treatment. We have many solutions for heat treatment steps, and I will present today what kind of solutions we are having and how we can enable our customers for additive manufacturing processes that can also be metal injection molding. We were talking about that already with all the other brands. Werder Scientific has so many solutions for additive manufacturing because this process is highly interdisciplinary. It starts from the raw material that is a powder, and that can be a ceramic powder or also a metallic powder. And it goes through many different steps until we have the final parts. And here we have a lot of solutions from Werder Scientific. I will focus now on the heat treatment part, which is, as I already mentioned, a step, a process step, which is highly underestimated. And I will tell you why. But first of all, a brief overview. How does it look? Additive manufacturing or metal injection molding, what are the different steps? It all starts with the raw material. And the raw material is always a powder. And this powder can be a metallic powder, but it can also be a ceramic powder. These kind of powders are mixed with the binder, and the so-called feedstock is generated. This can also be an extruded feedstock like you see here, or a granulate, which is mostly or most widely used for metal injection molding. Now the next step is the printing step, which is very important. And here we have a lot of different methods. It can be an injection molding machine, what is the more classical method, which is established in the industry since the early 70s. But nowadays, what becomes more and more popular and which becomes now an industrial application is the 3D printing. And there are so many different printing steps, that I just want to briefly mention one or two of them. It can be a fused filament printing process, or it can be a lithography-based step. Many different additive manufacturing processes and printers exist on the market. But they all have in common that the so-called green part is formed, which is a mixture of the polymer, which means the binder, and the powder. Of course, this green part is maybe 20 or even 30% bigger than the final part, because still we have the binder inside the green part. And now there are several ways to get rid of the binder. It can be a solvent debinding step, or it can be a thermal or a catalytic debinding step, where you see Carbolite Gero has machines in different sizes available. But it's not over. We need to have the next process step, that is the sintering step. And also here you see a lot of machines. They can be for metals, for the sintering of metal parts, or they can also be for the sintering of ceramic parts. And this step, or let's say this route of manufacturing, we call the so-called indirect method of additive manufacturing, because we are not going directly to the finished part, but we are going indirectly to the finished part via the green part, which is available as an intermediate part before the debinding and the sintering. This sounds complicated, but it offers a high variety of manufacturing methods, because also green parts you can further process, which is also highly interesting for many applications. So for this indirect method, Carbolite Gero offers the heat treatment solutions you need. But also for the direct method, and the direct method means that we go from the powder directly to the final part, and these additive manufacturing processes are well known and well established. It's electron beam melting, where an electron is focused to the part, or with laser powder bed fusion. Okay, here a laser is focused to the part and sinters it directly to final density, or to almost final density. Yeah, I mentioned it before, we have a focused spot. So that clearly indicates that you get tensions in the material, because the focus is only locally. We have a local focus of energy, and let's say the other sides, or the other sides of the part are still on a lower temperature. And that is basically the reason why you need to have a post-processing step in order to relieve the stress from the material which comes out of the manufacturing process. And also this is a heat treatment step, and here we have additional solutions from Carbolite Gero. So in additive manufacturing, you see heat treatment is really needed, although it's not in the focus of many users, but it's a very important step. And if you don't have precise machines, the best printer cannot manufacture good parts. Having a look at the materials, I mentioned it already. It can be metals, heat treatment for metals after additive manufacturing, but it can also be heat treatment of ceramics. And in ceramics, we distinguish non-oxide ceramics and oxide ceramics. Of course, the oxide ceramics, for instance, something like aluminium oxide or yttrium oxide. And on the non-oxide ceramic side, we talk about high-performance ceramics such as aluminium nitride or boronitride, silicon carbide, and so on and so on. On the metal side, you see the typical materials, the typical feedstocks which are available, but also titanium, of course, needs a heat treatment. And for both metals and ceramics, we offer the solutions of debinding and sintering with a very broad range of furnaces. I don't want to go into detail, but you can start with a simple tube furnace for research and development, let's say for smaller part production, or let's say for some trials. Next to that, you see an industrial machine for debinding and sintering in metal injection molding. It can also be that you do some kind of drying procedure before, where we have solutions here, the so-called PN oven from Carbolite Gero. So you see a range from small furnaces up to big furnaces used in the industry, both for metals, and here on the right-hand side, you see debinding and sintering furnaces for ceramics. We call this product line the Kappa product line, and it's basically our HTF. That would be an HTF, a chamber furnace for debinding and sintering, or our hood furnaces here. You see a hood furnace with a torch as a debinding solution in additive manufacturing. So for both metals and ceramics, you need heat treatment, and we can offer you the solutions for debinding and sintering. I start now to go a little bit into detail with the direct method of additive manufacturing. I mentioned it before. A laser or an electron beam is focused to print the final part. And here, of course, you see you have a high degree C of freedom in the manufacturing and in the design of the parts. That can really only be done by 3D printing by a laser or also by an electron beam. These parts need to be stress relieved. And of course, there is a norm which defines how this heat treatment has to be done. And we have two solutions here. The first solution is an industrial product which is used all over the world. It's for stress relief heat treatment up to a temperature of 1150 degrees C under a very high purity argon atmosphere. Of course, we measure the final oxygen content to really make a quality control of the process. So we have the oxygen value monitored and under control. This is our furnace. It's the GPCMA, a general purpose chamber furnace with modified atmosphere for high quality heat treatment of printed parts by a laser or by an electron. That's our first solution. This heat treatment is done under argon atmosphere, and we have a second solution where the same heat treatment can be done, but you have the option to do the process in high vacuum. So both furnaces for the same application, but this here is for atmospheric pressure, high purity argon, and this furnace is for high vacuum heat treatment. If you are interested in these products, we have a publication where we monitor the oxygen level and compare it between both furnaces by means of an EDX analysis. So now I go to the indirect method, and I told you before, the first thing in the indirect methods is the debinding. And the most important thing is we talk about two different kind of binders. We have the main binder, and the main binder is shown here with the yellow color between the powder particles. That is the main binder, and the main binder you get rid of by means of either a thermal debinding or a solvent debinding, or the example what we show in this case is a catalytic debinding. So what does it mean? We purge into that furnace nitric acid, HNO3. We evaporate the nitric acid. So we have a mixture of nitrogen and nitric acid, which is cycled over the parts by means of this fan. And this is the way how you catalytically get rid of the main binder. So the only thing that vanishes now by HNO3 catalytic debinding is the yellow main binder. So you see the parts coming out of these furnaces. The main binder is now gone, but the backbone binder, the orange bars here, still remain inside that part. And here we have a solution. This is an industrial scale solution. We have it in different sizes, and this is used all over the world, mainly for metal injection molding, but also for additive manufacturing. Yeah, I told you before, after this debinding step, with a solvent or with a catalyst, you still have the backbone binder in the system. And this backbone binder you can remove only by a thermal debinding step. And that is why the sintering furnaces, they have to perform two things. First of all, they need to remove the backbone binder. Yeah, the orange parts here need to be removed, and this normally happens between 400 and 600 degrees C. So this profile is highly important, and every time we talk about debinding and sintering, you will see such a profile. Because first, the backbone binder needs to be removed between 400 and 600 degrees C. And after this backbone binder is now removed, we need to sinter the part to the final density. So now the powder particles, they need to sinter together, and this happens 20% below the melting point of the material, yeah, and that is what you see here, 20% less than the melting point, you have a diffusion process. You also see it here, you have two powder particles, and by material diffusion, you sinter the part to its final density. And this is the most important thing to understand in 3D printing about debinding and sintering, because this is true when I talk about a metallic part, but also for ceramics, it's exactly the same. But of course, the atmospheres are different. So here I show you our heat treatment solution, the HTK for metal parts. So it's a metallic furnace, which you can use under different atmospheres, even an atmosphere of 100% pure hydrogen, which is required for very high quality parts, but also argon, nitrogen, vacuum. If the customer has special requirements, for instance, titanium, we can even equip this furnace with a high vacuum option, so you can do the whole sintering step also in high vacuum. Yeah, we have a safety concept for this furnace, and one thing that is very important, we just recently calculated the product carbon footprint, which becomes more and more important because of the high energy cost. These machines are highly energy efficient, even at its maximum temperature of 1400 degrees C. So this is our solution for metals, but we have similar solutions for debinding and sintering of ceramics. You see, we developed this product a lot. We even did CFD simulations. So we did some modeling of all the parts and simulated the gas flow to have the perfect condition both for debinding and sintering. Yeah, some examples. I only showed furnaces, but typical parts you can see here. In additive manufacturing, of course, the big advantage is the high complexity of the parts. You have now full freedom in design, which gives great opportunities. And I'm also sure that this field will grow a lot because those parts, imagine you would need to do turning and milling or something like that. The process would take endless time and also the costs would be very high. So for such kind of small parts with high complexity, additive manufacturing or metal injection molding is the process of choice, and our furnaces are the key to a successful part because, as you can imagine, uniformity of the temperature in the whole usable volume, gas management, these are all key parameters in order to get good and high quality parts. And here you see some of the examples. It even becomes more important because the automotive industry changes to electric motors. Now, if you have a look at some magnetic parts, at the moment, magnetic parts are very simple. But if you think about the possibilities here in additive manufacturing, there is so much opportunity for this kind of application. I'm already at the end. This was just just a small overview to give you an insight into the world of heat treatment in additive manufacturing. You see, we invested a lot. We simulated our systems to improve it. We reduced the product carbon footprint. We reduced the whole energy and gas consumption. And we were improving those kind of furnaces by means of CFD simulations. I want to thank you very much. Thanks a lot for your attention. And if you have any interest to go into detail, please contact us. We are always there for you. Thank you.
So thanks a lot, Tim, for introducing Carbolat Gero. And now we have our last slot for today, which is QATM. And here Parham Gemagami, member of the QATM Product Management and Application Technology team, will hold the presentation and tell us something about metallographic preparation as part of the quality control process in additive manufacturing. Parham, the word is yours.
Thank you, Reina, for a nice introduction. My name is Parham Gemagami, and I'm working as lab manager in Germany. And I will show you today the metallographic preparation of additive manufactured components. Yeah, here is the metallographic preparation as a part of quality control in additive manufacturing. Today, I will show you the additive manufacturing process very briefly, why it's important, the quality control of additive manufactured components, some images that we know what expectations should we have from the metallographic preparation, some hints and from the cutting of additive manufacturing components, some hints for mounting, and then we will go to the grinding and polishing, and then we will see the results for different materials. At the end, I will show you the hardness testing and the image analysis. Here is our lab in Mauthausen, Germany. In the left-hand side, you will see the cutting area from the table cut-off machines, and in the right-hand side, you can see the grinding and polishing area. At the very end of the lab, you can see the hardness testing and also image analysis. Now I want to introduce you briefly the additive manufacturing process. Here in additive manufacturing, in opposite to subtractive or formative manufacturing, we start from the design concept and then the parametric design. After that, we can analyze and optimize the parameters from the design concept and the creation of prototype. This prototype should be evaluated, and when it meets the design criteria, we can go to the final product, and otherwise we should start once again from these areas like design concept. Here in the right-hand side also, you can see we start from the 3D CAD, and then we go to the STL file, and then with the auxiliary geometries and machine and process parameters, we can optimize our process and go to the creation of prototype. On the left-hand side, you can see the different additive manufacturing processes. It can be liquid-based, solid-based, or powder-based. In the liquid-based, we can have the melting or polymerization, and in the powder-based also we can have the melting and binding. And the different additive manufacturing processes, you have seen also the names of them in different processes, and also you can be familiar with. On the right-hand side is an example for the additive manufacturing process. As you can see here, for example, we have the powder layer, and when the laser goes through the powder layer, we have the melt pool, and behind the laser, we have the solidified layer. Now, I will explain why additive manufacturing is important. Here in the left-hand side, you can see the global additive manufacturing market is something like $14 billion. And in the North America, from 2020 to 2023, and in the future to 2030, we can see always the constant growth in the market of additive manufacturing. In the bottom, you can see the dramatic rise in metallic additive manufacturing systems. And you can see the demand from the 2000 to 2017 increased dramatically. Here is an example for the quality control of additive manufacturing component. Here, the case is turbine blade. On the left-hand side, we have the manufacturing condition that in the traditional casting, we call it as cast condition. And here is a manufacturing condition. Here is the computer tomography and the hot isostatic press process A. The hot isostatic press with temperature 900 degrees. And the right-hand side, we have the temperature of 1220. And then we will see that, we want to see that which one is better. Here at the left-hand side, we should have the defect detection. It means that the location and extent of the defect. And then the macrostructure in the defect area and hardness in the defect area. And at the end, tomography and elemental composition in the defect area. We should do this evaluation for each of these processes, and then we compare them together. Here, as you can see, the microstructure and hardness we should do on a hardness tester and optical microscope, and tomography and elemental composition should be done under scanning electron microscope. Here is the area of interest for us. The metallographic preparation here plays a very important role. What do we expect to analyze? Here is some images from literature that also you can find the references later on the file of presentation. On the left-hand side, we can see the pore measuring under optical microscope, and left-hand side is a pore under scanning electron microscope. On the left-hand side, you can see the pores under optical microscope, and also some other defects we can meet here, something like not melted reagents. Also on the left-hand side here, you can see the pores under the optical microscope and also the laser layers under the stereo microscope. With this introduction, I want to start from the cutting process. We should be aware that the properties on the additive manufactured samples is not isotropy, is anisotropy. It means that on different directions, we have the different mechanical and physical and microstructural properties. Here we can see, for example, the microstructure of longitudinal selective laser melting and the right-hand side horizontally. And below you can see the longitudinal electron beam melting microstructure in compare with horizontally. And they are different from each other. And we should be aware that which direction should be evaluated. Here is some hints for cutting process. At the left-hand side, you can see that choosing the right cutoff disc is very important. We have the different cutoff discs for different materials. For example, aluminum oxide, silicon carbide, as well as diamond and CBN cutoff discs. And also choosing the right clamping tool. For example, here you can see the Q-Tool 40S is a manual clamping tool that you can fix your sample with the manual force, and is very good for the porous material that they are not very stable. To cut the porous material, always is a good idea to mount the sample before cutting. Now some hints for mounting process. We can use the cold mounting for porous samples. Here you can see the Cupox 92 and Cupox 94. They are the epoxy resin based cold mounting material because the porous samples are sensitive to the temperature and also pressure. On the right hand side, you can see the hot mounting, the Epo Black for the non-porous samples. Also, you can use the mounting accessories for tiny samples to fix them on the surface of the sample. Here we have the, for example, steel clips and also plastic clips from different types and for different shape of materials. Now I want to start for grinding and polishing and show you the preparation methods for different materials. I start from the maraging steel. Here you can see that we start the grinding with Polaris H. Polaris H is a diamond grinding disc with the diamond abrasive particles and resin between them. Very shortly, we can have the very plain surface and start with polishing with beta 9 micrometer, gamma 3 micrometer, and omega for final polishing. We etch the samples with 3% alcoholic nitric acid for just 5 seconds. After that, we can see the structure under a stereo microscope. And as you can see here in the low magnification, we can see the outline, white, an outline pattern, and also the spacing between the outline and our pattern. When we are going to the higher magnification, we can see the spacing between the pattern and also the pattern angle, and different parameters also can be measured on these stereo microscope images. When we are going to the optical microscope, we can see the laser layers under the microscope and also the grain boundaries and also the boundary between the laser layers. Here, to have a very clear boundaries is very important to not have the deformation and have a right metallographic preparation. And because of that, the metallographic preparation with right material, consumables, and also right parameters is very important. Now I will show you the preparation method of additive manufactured aluminum silicon alloy. Here we use the SiC grinding paper, but with no elasticity and lower elasticity, because here at the right hand side you can see the working plate, magnet foil, and on the magnet foil you can have the grinding disc or adapter disc. Here, the adapter disc between the SiC paper and working plate is a quick tap. Quick tap is an adapter disc with a metallic bag, and also you can use the SiC grind paper, the normal paper on it with the low viscosity. Here we use the P320 and P1200 for grinding, and after that 3 micron and 1 micron for polishing. For etching, we use the scroll etchant for 30 seconds. Now you can see the edge without rounding in the not etching position, and also on the right hand side we can do the core area. After etching, we can see the outline and also pattern and the spacing between the outline and pattern, and also the different laser layers under optical microscope. Quickly, I introduce you the preparation method of copper alloys, the additive manufactured copper alloys. Here is the parameters. Once again, we use the SiC paper P320, P1200 for the grinding, and then sigma for 3 micron and theta for 1 micron, and shortly for 4 minutes final polishing. Here you can see the structure of the sigma polishing cloth is a wool polishing cloth, and you can use it for 3 micron. The etchant here is copper A. After etching, you can see the edge of the material, the outline without any rounding. Then you can see the coarse grains on the edge of the sample, and on the core area you can see the fine grains. To see the grain boundaries between these grains is very important to not have deformation on your preparation. The metallographic preparation is very important here to have a very clear grain boundaries. Here also on the left hand side we can see the area with the finer grains, and also here you can see very clear the grain boundaries between the different grains. Now I can show you the preparation method of additive manufacturing titanium alloys. Once again, for grinding SiC paper P320 and P800 this time, and here is very important to have the final polishing a bit longer, just like 8 minutes. Here you can see some words like poly, for example, diamond suspension poly or mono, or some words like this. I want to show you what does it mean. On the right hand side, you can see the monocrystalline of diamond and polycrystalline. As you can see, the polycrystal has more edges and is more aggressive than monocrystal. And to use the polycrystal is very important to have the right dosing parameters. For example, here you can see the dosing interval and dosing time for 3 micron and 1 micron is every 30 seconds for 1.5 seconds. Here is the microstructure of titanium alloy under the optical microscope, under lower magnification on the left-hand side and higher magnification on the right-hand side. Also, we can see some defects here, something like lack of fusion or some pores that we can see on the lower and on the right-hand side and the higher magnification. Here, the lack of fusion on the grain boundaries can be seen on the left-hand side very clearly, and also we can see the edge of the sample without any rounding and without any gap between the material and mounting material on the right-hand side. Also, when we put this titanium sample under stereo microscope, we can see once again the laser layers, outline, and patterns. On the higher magnification, also you can measure the outline width and also the spacing between the outline and pattern, and also the pattern angle. Here on the left-hand side of the titanium additive manufactured sample, you can see the 3D microstructure of the pore within the pore, and on the right hand side you can see the boundary between two different microstructures. And here once again you can see the edge of the additive manufacture samples without any gap and without any rounding. Now I want to show you the hardness testing on the additive manufactured components. Here you can see the different Vickers hardness indenters from the 10 gram to 100 gram on the one laser layer. We can do also the hardness testing on the grain boundary or in the laser layer boundaries on the different laser layers to compare them together. These tests have been done with QNES 68+. As you can see here on the revolver, you have the different objectives, and also you can put your sample individually or on the sample holder under the hardness tester. And it's a good advantage of this hardness tester that you can put your samples within the sample holder under the hardness tester. Also, an example from the image analysis. On the left-hand side, you can see the pores on the surface of the sample, and on the right-hand side, you can see the image analysis and the porosity percentage that was measured by our software. Here you can see 2.8% of porosity we have on the surface of the sample. Here, to measure the porosity percent is very important to not smear the material on the pores, to not cover and close the pores. And here the metallographic preparation and the right metallographic preparation is very important. With this image analysis, I come to end of my presentation. I want to thank you for your attention and wish you a nice day.
Yeah, thank you, Paham. So I think we are at the end of our webinar for today. I'd like to thank every one of you for participating and listening to us, taking the time. And if you have any questions, please do get in touch with us, visit our website, subscribe to our newsletter, and if we can help, just get in touch with us. In the next days, you will get a link, a download link for a video of this webinar and some other interesting material. And yeah, so have a nice day, and I hope to see you soon again. Bye-bye.